This lecture introduces Chapter 24. We will continue our study of electric fields, and in this chapter, you will learn about and apply Gauss's law. Suppose we know only two things. The field points away from positive charges toward negative charges, and an electric field exerts a force on a charged particle. From this information alone, what can we deduce about the electric field of an infinitely long charged cylinder? We don't know if the cylinder's diameter is large or small. We don't know if the charge density is the same as the outer edge as along the axis. All we know is that the charge is positive and that the charge distribution has cylindrical symmetry. We say that a charge distribution is symmetric if there is a group of geometric transformations that don't cause any physical change. A charge distribution can have symmetry in one of the following three ways: translation, rotation, or reflection. An infinitely long charged cylinder is symmetric with respect to translation parallel to the cylinder axis. Shifting an infinitely long cylinder by 1 millimeter or 1,000 meters makes no noticeable or measurable change. Rotation by an angle about the cylinder axis. Turning a cylinder about its axis by 1 degree or 100 degrees makes no detectable change. Reflections in any plane containing or perpendicular to the cylinder axis. Exchanging top and bottom, front and back, or left and right makes no detectable change. A charge distribution that is symmetric under these three groups of geometric transformation is said to be cylindrically symmetric. Other charge distributions have other types of symmetries. Some charge distributions have no symmetry at all. Our interest in symmetry can be summed up in a single statement. The symmetry of the electric field must match the symmetry of the charge distribution. This reflection, which does not make any change in the charge distribution itself, does change the electric field. Therefore, the electric field of the cylindrically symmetric charge distribution cannot have a component parallel to the cylinder axis. Could the field look like the figure below? Here we are looking down the axis of the cylinder. The next slide shows what the field would look like reflected in a plane containing the axis, left to right. This reflection, which does not make any change in the charge distribution itself, does change the electric field. Therefore, the electric field of a cylindrically symmetric charge distribution cannot have a component tangent to the circular cross-section. Based on symmetry arguments alone, an infinitely long charged cylinder must have a radial electric field as shown below. This is one electric field shape that matches the symmetry of the charge distribution. There are three fundamental symmetries. The first is planar symmetry. Planar symmetry involves symmetry with respect to translation parallel to the plane, rotation about any line perpendicular to the plane, and reflection in the plane. The second is cylindrical symmetry. Cylindrical symmetry involves symmetry with respect to translation parallel to the axis, rotation about the axis, reflection in any plane containing or perpendicular to the axis. The third is spherical symmetry. Spherical symmetry involves symmetry with respect to rotation about any axis that passes through the central point, and reflection in any plane containing a center point. If you are wondering why we spend so much time discussing symmetry, it is because symmetry arguments allows us to rule out many conceivable field shapes as simply being incompatible with the symmetry of the charge distribution. Knowing what doesn't happen or can happen is often as useful as knowing what does happen. By the process of elimination, we're led to the one and only shape that field can possibly have. Reasoning on the basis of symmetry sometimes is subtle, but always powerful means of reasoning. Consider a box surrounding a region of space. We can't see into the box, but we know there is an outward pointing electric field passing through every surface. Since electric fields point away from positive charges, we can conclude that the box must contain net positive electric charge. Consider another box surrounding a region of space. We can't see into the box, but we know that there's an inward pointing electric field passing through every surface. Since electric fields point toward negative charges, we can conclude that the box must contain net negative electric charge. Consider a third box surrounding a region of space. We can't see into the box, but we know that the electric field points into the box on the left, and an equal electric field points out of the box on the right. Since the electric field is not altered by the contents of the box must contain zero net electric charge. Suppose we surround a region of space with a closed surface, a surface that divides space into distinct inside and outside regions. Within the context of electrostatics, a closed surface through which an electric field passes is called a Gaussian surface, named after the 19th century mathematician Carl Gauss. This is an imaginary mathematical surface, not a physical surface, although it might coincide with a physical surface. A closed surface must, of necessity, be a surface in 3 dimensions, but 3-dimensional pictures are hard to draw. So we'll often look at 2-dimensional cross-sections through a Gaussian surface. A Gaussian surface is most useful when it matches the shape and symmetry of the field. Figure A shows a cylindrical Gaussian surface. Figure B simplifies the drawing by showing 2-dimensional end and side views. The electric field is everywhere perpendicular to the side walls, and no field passes through the top and bottom surfaces. Not every surface is useful for learning about charge. Consider the spherical surface in the figure. This is a Gaussian surface, and the protruding electric field tells us there's a positive charge inside. It might be a point charge located on the left side, but we can't really say. A Gaussian surface that doesn't match the symmetry of the charge distribution isn't terribly useful. These examples lead us to 2 conclusions. The electric field in some sense flows out of a closed surface surrounding a region of space containing a net positive charge and into a closed surface surrounding a net negative charge. The electric field may flow through a closed surface surrounding a region of space in which there is no net charge, but the net flow is 0. The electric field pattern through the surface is particularly simple if the closed surface matches the symmetry of the charge distribution inside. The electric field doesn't really flow like a fluid, but the metaphor is a useful one. The Latin word for flow is flux, and the amount of electric field passing through a surface is called the electric flux. Our first conclusions stated in terms of electric flux are: there is an outward flux through a closed surface around a net positive charge. There's an inward flux through a closed surface around a net negative charge. There is no net flux through a closed surface around a region of space in which there is no net charge. Imagine holding the rectangular wire loop of area A in front of a fan. The volume of air flowing through the loop each second depends on the angle between the loop and the direction of flow. The flow is maximum through a loop that is perpendicular to the airflow. Imagine holding a rectangular wire loop of area A in front of a fan. No air goes through the same loop if it lies parallel to the flow. The volume of air flowing through the loop each second depends on the angle theta between the loop normal and the velocity of the air and is equal to the perpendicular component of the velocity times the area. This is similar to the continuity equation when we learn about hydrodynamics, where we only consider perpendicular flows of a fluid. The electric flux, phi, measures the amount of electric field passing through a surface of area A, whose normal to the surface is tilted at an angle theta from the field and is equal to the electric field times the projected surface area. Mathematically, the flux of a non-uniform field through a curved surface is described by a special kind of integral, called a surface integral. The electric flux through the shaded surface is the answer is C, 400 Newton meters squared per coulomb. We're multiplying the electric field by the area of the surface. The electric field through the shaded surface is A, 0. The electric field is perpendicular to the normal of the surface. The electric flux through the shaded surface is the answer is C. The projected area of the surface is the area times the cosine of the angle, and the angle is 70 degrees. Let's define an area vector A to be a vector in the direction of the surface normal, perpendicular to the surface with a magnitude equal to the area of the surface. The area vector has units of meters squared. An electric field passes through a surface of area A. The electric flux can be defined as the dot product E dot A. Writing the flux as a dot product helps us make clear how angle theta is defined. Theta is the angle between the electric field and the line perpendicular to the plane of the surface. Two 100 square centimeter parallel electrodes are spaced 2 centimeters apart. One is charged plus 5 nanocoulombs, the other to minus 5 nanocoulombs. A 1 centimeter by 1 centimeter surface between the electrodes is tilted towards normal, makes a 45-degree angle with the electric field. What is the electric flux through the surface? Assume the surface is located near the center of the capacitor where the electric field is uniform. The electric flux doesn't depend on the shape of the surface. Consider the drawing. The surface is square rather than circular, but otherwise the situation looks like the figure. Between the parallel plates, the electric field is uniform and given as the charge divided by epsilon naught times A. Since the field, the area, and the angle are all known, it is a simple matter to calculate the flux. Consider a surface in a non-uniform electric field. Divide the surface into many small pieces of area delta A. The electric flux through each small piece is the electric field at that piece times the surface area. The total electric flux through the entire surface is then the sum of the fluxes through each of the small areas. Let the areas become infinitesimally small, and there are infinitely many of them. Then the sum becomes an integral, and the electric flux through the whole surface is the surface integral of E dot dA. The electric field might be different at every point on the surface, but suppose it isn't. That is, suppose a flat surface is a uniform electric field. The integral simplifies to E times A cosine of theta, as found earlier. Most of the Gaussian surfaces we considered in the last section were curved surfaces. The figure shows an electric field passing through a curved surface. How do we find the electric flux through this surface? Well, the same as before. Divide the surface into many small pieces of area delta A. Find the electric flux through each small piece, sum over all pieces, and create the same surface integral. Consider an electric field that is everywhere tangent or parallel to a curved surface. E dot dA is 0 at every point on the surface because E is perpendicular to dA at every point. Therefore, the electric flux is 0. Consider an electric field that is everywhere perpendicular to the surface and has the same magnitude E at every point. In this case, the flux is just E times A. To evaluate surface integrals, if the electric field is everywhere tangent to the surface, the electric flux through the surface is 0. If the electric field is everywhere perpendicular to the surface and has the same magnitude E at every point, the electric flux through the surface is just E times A. Surfaces A and B have the same shape and the same area. Which has the larger electric flux? The answer is A. While the two areas are the same, the strength of the electric field, as shown by the separation of the electric field lines, is less at B than at A. So A has the larger flux. Which surface, A or B, has the larger electric flux? The answer is C. The fluxes are equal. The electric field strength is constant. B has a larger area, but that is countered by the cosine of the angle. The projected area is the same for both surfaces. We've already learned how to calculate the electric flux through flat and curved surfaces, and a closed surface is nothing more than a surface that happens to be closed. It is customary to use a little circle on the integral sign to indicate that the surface integral is to be performed over a closed surface. With this notation, the electric flux through a closed surface is the integral shown. The electric flux is still the summation of the fluxes through a vast number of tiny pieces that now cover a closed surface. Note, for a closed surface, we use the convention that the area vector dA is defined to always point toward the outside. To find the flux through a closed surface, choose a Gaussian surface made up of pieces that are everywhere tangent to the electric field or everywhere perpendicular to the electric field. Use the earlier tactics box to evaluate the surface integrals over these surfaces, then add the results. These are cross-sections of 3D closed surfaces. The top and bottom surfaces, which are flat, are in front of and behind the screen. The electric field is everywhere parallel to the screen. Which closed surface or surfaces have zero electric flux? The answer is A. For object B, the electric field points everywhere outside, so the flux cannot be zero. For object C, the electric field points everywhere inside, so the flux cannot be zero. For object A, the flux in equals the flux out of the surface, and the net electric flux is zero. The purpose of learning Gauss's law is twofold. Gauss's law allows us the electric fields of some continuous distributions of charge to be found much more easily than does Coulomb's law. Gauss's law is valid for moving charges, but Coulomb's law is not, although it's a very good approximation for velocities that are much less than the speed of light. Thus, Gauss's law is ultimately a more fundamental statement about electric fields than is Coulomb's law. Let's start with Coulomb's law for the electric field of a point charge. The figure shows a spherical Gaussian surface of radius r centered on a positive charge q. Keep in mind that this is an imaginary mathematical surface, not a physical surface. There is a net flux through the surface because the electric field points outward at every point on the surface. To evaluate the flux, given formally by the surface integral, notice that the electric field is perpendicular to the surface at every point on the surface, and from Coulomb's law, it has the same magnitude, q over 4 pi epsilon naught r squared. This simple situation arises because the Gaussian surface has the same symmetry as the electric field. The surface area of the sphere is 4 pi r squared. The flux is then simply q over epsilon naught. The electric flux through a spherical surface centered on a single positive point charge is q over epsilon naught. This depends on the amount of charge, but not on the radius of the sphere. For a point charge, the electric flux is independent of r. As the diagram shows, every field line emanating from the point charge passes through both spheres. Think of the fluid analogy with which we introduced the term flux. If fluid flows outward from the central point, all the fluid crossing the small radius of spherical surface will, at some later time, cross a large radius spherical surface. No fluid is lost along the way, and no new fluid is created. Similarly, the point charge in the figure is the only source of the electric field. Every electric field line passing through a small radius spherical surface also passes through a large radius spherical surface. Hence, the electric flux is independent of r. The electric flux through an arbitrary closed surface surrounding a point charge q may be broken up into spherical and radial pieces. The electric field is everywhere tangent to the radial piece. Hence, the electric field through the radial piece is zero. The spherical pieces, although at varying distance from the charge, form a complete sphere. That is, any line drawn radially outward from the charge will pass through exactly one spherical piece, and no radial line can avoid passing through a spherical piece. You can even imagine, as the figure shows, sliding the spherical pieces in and out without changing the angle they subtend until they come together to form a complete sphere. The total flux through the spherical pieces must be the same as through a single sphere. The closed surface shown in the figure has a point charge Q outside the surface, but no charges inside. The electric flux through any arbitrary closed surface entirely outside a point charge Q may also be broken up into spherical and radial pieces. If the electric field were a fluid flowing outward from the charge, all the fluid entering the closed region through the first spherical surface would later exit the region through the second spherical surface. There is no net flow into or out of the closed region. Similarly, every electric field line entering this closed volume through one spherical surface exits through the other spherical surface. Mathematically, the electric fluxes through the two spherical surfaces have the same magnitude because the flux is independent of r, but they have opposite signs because the outward pointing area vector is parallel to the electric field on one surface, but opposite to the electric field on the other. The sum of the fluxes through the two surfaces is 0. We conclude that the total flux through the concave and convex spherical pieces must cancel each other. The net electric flux is 0 through a closed surface that does not contain any net charge. Consider an arbitrary Gaussian surface that contains a group of charges Q1, Q2, Q3, and so on. The contribution for any charge outside of the surface is 0. The contribution to the total flux for any charge inside the surface is Q sub I over epsilon naught. From the principle of superposition, the total electric field is the sum of the individual electric fields from each charge. The total flux then must be the sum of the individual fluxes of each field produced by each charge. Defining Qn to be the sum of all the charge inside the surface, we find the total flux to be Qn divided by epsilon naught. For any closed surface enclosing total charge Qn, the net electric flux through the surface is Qn divided by epsilon naught. This result for the electric flux is known as Gauss's law. The electric field is constant over each face of the box. The box contains The answer is B. The areas are the same for each face. The flux is the sum of the electric field times the area. The sum of the electric field yields a net negative or inward pointing electric field, which means the net charge must be negative. Which spherical Gaussian surface has the larger electric flux? The answer is B. Surface B has more enclosed charge. Spherical Gaussian surface of equal radius r surrounding two spheres of equal charge q. Which Gaussian surface has the larger electric field? The answer is C. They have the same enclosed charge. Three important observations can be made about using Gauss's law. Gauss's law applies only to a closed surface called a Gaussian surface. A Gaussian surface is not a physical surface. It need not coincide with the boundary of any physical object, although it could if we wished. It is an imaginary mathematical surface in the space surrounding one or more charges. We can't find the electric field from Gauss's law alone. We need to apply Gauss's law in situations where, from symmetry and superposition, we already can guess the shape of the field. To solve Gauss's law problems, model the charge distribution as a distribution with symmetry. Draw a picture of the charge distribution. Determine the symmetry of the electric field. Choose and draw a Gaussian surface with the same symmetry. You need not enclose all the charge within the Gaussian surface. Be sure every part of the Gaussian surface is either tangent to or perpendicular to the electric field. Use the mathematical representation is based on Gauss's law. Check that your results have correct units and significant figures, is reasonable, and answers the question. A spherical Gaussian surface surrounds an electric dipole. The net enclosed charge is 0, which is true. The answer is B. The flux is 0, but that doesn't require the field to be 0. The electric flux is shown through two Gaussian surfaces. In terms of Q, what are the charges Q1 and Q2? The answer is C. The first surface has one charge, so the total charge inside is 2Q. The second surface has two charges, Q1 and Q2, which sum to Q. This gives us a set of simultaneous equations. Solving the system of equations gives Q1 is equal to 2Q and Q2 is equal to minus Q. In chapter 23, we asserted without proof that the electric field outside the sphere of total charge Q is the same as the field of point charge Q at the center. Use Gauss's law to prove this result. The charge distribution within the sphere need not be uniform. The charge density might increase or decrease with R, but it must have a spherical symmetry in order for us to use Gauss's law. We will assume that it does. The figure shows a spherical Gaussian surface surrounding a sphere of charge. The figure on the previous slide shows a sphere of charge Q of radius r. We want to find the electric field outside the sphere for distances r greater than r. The spherical symmetry of the charge distribution tells us that the electric field must point radially outward from the sphere. Although Gauss's law is true for any surface surrounding the charged sphere, it is useful only if we choose a Gaussian surface to match the spherical symmetry of the charge distribution and the field. Thus, a spherical surface of radius r greater than r, concentric with the charged sphere, will be our Gaussian surface. Because this surface surrounds the entire sphere of charge, the enclosed charge is simply Q. To calculate the flux, use Gauss's law and notice that the electric field is everywhere perpendicular to the spherical surface. And although we don't know the electric field magnitude E, spherical symmetry dictates that E must have the same value at all points equally distant from the center of the sphere. The surface area of the sphere is 4 pi r squared, so the flux is 4 pi r squared times E. The charge enclosed is Q, so the electric field outside the sphere can be found as pointing radially away from the sphere with a magnitude of 1 over 4 pi epsilon naught Q over r squared. The field is exactly that of a point charge Q, which is what we wanted to show. The derivation of the electric field of a sphere of charge depended crucially on a proper choice of the Gaussian surface. We would not have been able to evaluate the flux integral so simply for any other choice of surface. The book has two more examples, 24.2, the electric field inside a uniformly charged sphere, and 24.5, the electric field of a long charged wire. You should follow these examples. As another example, use Gauss's law to find the electric field of an infinite plane of charge with surface charge density eta. A uniformly charged flat electrode can be modeled as an infinite plane of charge. The figure shows a uniformly charged plane with surface charge density eta. We will assume that the plane extends infinitely far in all directions. The planar symmetry allows the electric field to point only straight toward or away from the plane. With this in mind, choose a Gaussian surface of a cylinder with length L and faces of area A, centered on the plane of charge. The electric field is perpendicular to both faces of the cylinder, so the total flux through both faces is 2EA. The fluxes add rather than cancel because the area vector A points outward on each face. There is no flux through the wall of the cylinder because the field vectors are tangent to the wall. The charge inside the cylinder is that of the charge contained in the area A of the plane, which is the surface charge density times the area. The electric field due to an infinite plane of charge is the surface charge density divided by 2 epsilon naught. This is another example of a Gaussian surface enclosing only some of the charge. Most of the plane's charge is outside the Gaussian surface and does not contribute to the flux, but it does affect the shape of the field. We wouldn't have planar symmetry with the electric field exactly perpendicular to the plane, without all the rest of the charge on the plane. A cylindrical Gaussian surface surrounds an infinite line of charge. The flux through the two flat ends of the cylinder is The answer is A. The electric field is perpendicular to the area vector, yielding 0. A cylindrical Gaussian surface surrounds an infinite line of charge. The flux through the wall of the cylinder is The answer is B. The electric field is parallel to the area vector. Using Gauss's law and that the lateral surface area of a cylinder is 2 pi RL gives a flux of 2 pi RL times E. The figure shows a Gaussian surface just inside a conductor surface. The electric field must be 0 at all points within the conductor, or else the electric field would cause the charge carriers to move, and it wouldn't be in equilibrium. By Gauss's law, Q inside is equal to 0. The external electric field right at the surface of a conductor must be perpendicular to that surface. If it were to have a tangential component, it would exert a force on the surface charges and cause a surface current, and the conductor would not be in electrostatic equilibrium. A Gaussian surface extending through the surface of a conductor has a flux only through the outer face. The net flux is Qn divided by epsilon naught. Here Qn is eta times the surface area, so the electric field at the surface of a conductor is eta over epsilon naught, perpendicular to the surface. A point charge Q is located distance r from the center of a neutral metal sphere. The electric field at the center of the sphere is The answer is D. Draw a spherical Gaussian surface around the sphere. The total enclosed charge is 0, so the electric field must be 0. The figure shows a charged conductor with a hole inside. Since the electric field is 0 inside the conductor, we must conclude that Qn equals 0 for the interior surface. Furthermore, since there's no electric field inside the conductor and no charge inside the hole, the electric field in the hole must also be 0. Suppose we need to exclude the electric field from the region in Figure A, enclosed within the dashed lines. We can do so by surrounding this region with a neutral conducting box shown in B. This region of space is now a hole inside a conductor. Thus, the interior electric field is 0. The use of a conducting box to exclude electric fields from a region of space is called screening. Solid metal walls are ideal, but in practice, wire screen or wire mesh, sometimes called the Faraday cage, provides sufficient screening for all but the most sensitive applications. The figure shows a charge Q inside a hole within a neutral conductor. Net charge minus Q moves to the inner surface, and net charge plus Q is left behind on the exterior surface. Charge plus 3 nanocoulombs is in a hollow cavity inside a large chunk of metal that is electrically neutral. The total charge on the exterior surface of the metal is The answer is B. A Gaussian surface drawn in the hollow cavity encloses a total charge of plus 3 nanocoulombs. Anywhere inside the neutral metal, the electric field must be 0, meaning that no net charge must be inside a Gaussian surface. There must be a charge of minus 3 nanocoulombs on the inner surface of the cavity. A Gaussian surface drawn outside the metal can only contain a total of plus 3 nanocoulombs. There must be a charge of plus 3 nanocoulombs on the outside of the metal to cancel the minus 3 nanocoulombs on the inside surface. Adding the contribution yields plus 3 nanocoulombs. To find the electric field of a conductor in an electrostatic equilibrium, the electric field is 0 at all points within the volume of the conductor. Any excess charge resides entirely on the exterior surface. The external electric field at the surface of a charged conductor is perpendicular to the surface and of magnitude eta over epsilon naught, where eta is the surface charge density at that point. The electric field is 0 inside any hole within a conductor unless there is a charge in the hole. A 2 centimeter diameter brass sphere has been given a charge of 2 nanocoulombs. What is the electric field strength at the surface? Brass is a conductor. The excess charge resides on the surface. The charge distribution has spherical symmetry. The electric field points radially outward from the surface. We can solve this problem in two ways. One uses the fact that a sphere, because of its complete symmetry, is the only shape for when the excess charge will spread up to a uniform surface charge density. The surface charge density is 1.59 times 10 to the minus 6 coulombs per square meter. The electric field must be 1.8 times 10 to the 5 newtons per coulomb. Alternatively, we could have used the results obtained early in the chapter, that the electric field strength outside the sphere of charge Q is the same as a point charge, and since the charge and size of the sphere are known, yields the same result. We will do additional examples in class.